And Shalini, I can only guess that you're asking about me recording for a friend. So that's what makes you such a good classmate. So thank you again. All right, you guys, you know what? I tell you what, I feel like I'm talking to myself because I'm looking at just a bunch of black boxes with your names on it. So you guys gotta, you know, I get it. If you don't want to turn your camera on or whatever, that's totally fine. But you just remember, all I can rely on is the chat. Okay, or you guys actually saying something. So if something is awry, you know, if you can't see something or if my sound is not good, you guys just gotta let me know. All right, well, you guys know I like to start on time, so I'm still admitting people, but I would love for you guys to start throwing out your questions. So, you know, what do you have interest in? What do you have concerns about? I think just in general terms, the assessment on Thursday is going to be just like the usual format. It's going to be 11 multiple choice. No surprises this time. I assure you that you cannot use a calculator for the multiple choice. So make sure that with the no calc practice that you guys are really practicing doing all the calculations without a calculator. And then one big short answer. So just one question, and I believe it's parts like A through G. Okay, so that's not too bad, right? Okay, so you guys, I'm going to start checking on the chat. And if you guys kind of see me looking to the side, that's because I have my other computer open and that's where I'm reading the chat. So if it looks weird, that's why. Still letting people in. Okay, so the first question I see is, do you mind explaining mechanisms? We really didn't talk too much about it. Okay, I agree. We have to do a problem with R squared. All right, so that's another issue. These are great questions, so keep them coming in and give me a few things to think about. I see.
Hey, Miss Ann. How are you?
I see some interesting people there.
Yes, you do. Bye.
Sarah, if you're talking to me, just so you know, I can't hear you, so. Okay, so Arrhenius equation, I'm writing down some of the things you guys are talking about. Okay, so number one, yes, you get to use the formula sheet. And if you look at the formula sheet, it has all the integrated rate laws. It also has the half-life for first order. And it does not have the Arrhenius equation, but we will give you that. So you do not have to memorize the Arrhenius equation. Okay, so we might as well start. Let's see. Yeah, I'm going to go ahead and share my screen. And again, hello, if you guys came in a little late, it's great to see all of you. Well, kind of see all of you. It's great to see all your names pop up. Okay, looks like we have about 42 of us with us today. All right, and I'm just gonna kind of waltz through the chat feature. Okay, so first thing I heard a question about was, how do you use the Arrhenius equation? Okay, so you guys, what I really want you guys to know about the Arrhenius equation is that it looks something like this. Okay, so natural log K equals negative EA over R over T plus natural log A. So that is the form of the Arrhenius equation that I would say that you want to know. Okay, and the reason why we like this form of the Arrhenius equation is because it produces a linear relationship. So it follows the format y equals mx plus b. Okay, so what that would look like is if you were to do a graph, so basically what it would look like if you did an experiment. So basically you would run an experiment at like multiple different temperatures. So let's say we had that light stick reaction. You would run the light stick reaction at like 0 degrees, 25 degrees, and maybe like 60 degrees. So pick 3 temperatures or more. Okay, and then for each of those temperatures, you would have a different rate. Of course, when you increase the temp, the rate goes up. From that, you'd calculate K. So your data table would basically look like 3 temperature values, 3 K values. But when you plot it, you would plot on the y-axis, natural log of K. And then on the x-axis, if I kind of break this down a little bit, I'm going to put the constants together. Whoops. So like EA over R minus is going to go together, and then 1 over T is the variable that you can change. So that's going to go on the x-axis. So it's going to look something like that. So that's the key with the Arrhenius equation. In order to get a linear relationship, you plot natural log of K versus 1 over temp. Okay, and please make sure the temp is in Kelvin. Okay, and then you will get a negative slope, a beautiful straight line. Okay, and then of course, like your calculator or like an owl did it for you. It calculated the slope, and the slope equals EA over R. So basically, the Arrhenius equation in this experiment is the only experimental method we have to calculate the activation energy. So if you want to get EA by itself, you would multiply it both sides by R. Okay, and then just basically move the negative over. Okay, so negative R times that slope would equal the activation energy. And the units for that would be in joules. So you might have to convert it to kilojoules. Okay, another question. Ooh, hi. So somebody said, we can't see your work. Ah, you can't see what I'm writing. See, that's why you guys are so helpful. Interesting, I wonder why not. You're sharing the screen. Okay, So you guys, can anybody, I can see it, we can see it, uh-oh. Okay, Okay, so can anybody still not see my writing? Okay, so Shyla, I guess go ahead and try that. I'll look for you and I'll be sure to let you right back in, okay? All right, so hopefully we're good. Thank you for letting me know. Okay, so back to this problem. So that would be the experiment. You would plot, you just run an experiment at different temperatures, you calculate the different K values, and then the slope would be how you could calculate EA. Oh, I know what the point was I was gonna make. Is somebody asked about the A value. So, there we go. So there we go. So A, right here, that's called the frequency factor. And honestly, you don't have to know much about it, except that the frequency factor has to do with correct orientation. So Ms. Schneider and I, we both talked about how some collisions are very sensitive to how they collide, being the correct orientation, like that little popper that we had. If you dropped it the wrong way, you didn't get the same reaction. Okay, so you had to collide it a certain way. So the more sensitive a reaction is to orientation, the bigger the A value is going to be. So you could get that. That's also just something else you could get off the graph. It would be the y-intercept. But remember, it would be natural log of A. So in order to get A by itself, you would do E to that number, okay? But for the most part, I don't think you have to worry too much about it, except that you've heard it, okay? So let's see, what other questions? Oh, good. So everybody can see the writing. What other questions do we have about the Arrhenius equation? I'm just gonna kind of look through the chat. Let's see, graphing calculator. Okay, I think we're good. So it says, how do we calculate the K value from the Arrhenius problem table? Not really quite sure what you're getting at, but I don't think that would come up, okay? Because for this data, you would have the K values, you would have the temperature, okay? So I would just say that the Arrhenius equation is a tool that you can use to experimentally determine the activation energy, okay? And that's what I would know about it. Okay, so let's see, I think we can probably leave the Arrhenius equation. Let me make sure I didn't miss anything in the chat. Okay, some quick things. So some of you guys asked about R squared. You know what, I'm not gonna, so here's the story. You should be able to do your assessment on Thursday or Friday without a graphing calculator. So I'm not gonna ask you to graph anything, but what I could do is kind of like that quiz that you guys took the other day, is I might give you the graphs, okay? Or I might describe some data. So if I give you like 3 graphs, you know, and it's like a curve, and then one of them straight, you know, and this one happens to be, you know, concentration versus time. This is like natural log of concentration versus time, and this is 1 over concentration versus time. So it looks something like that. So if I gave you some data and I said, well, you know, the R squared value for this one is, you know, 0.9999999, and it looks straight, then you would conclude that you know, that was the right graph. So yeah, you guys got some practice with graphing, but honestly, you know, we're not going to take time during the test to have you, you know, demonstrating that you can use your graphing calculators, okay? So I would either give you the graphs or I would describe what I saw on the graphs in words, okay? So that's what you guys can expect to see for that. All right, let's see what other questions that we have. I'm looking over here in the chat. Okay, I think I'm missing some of the questions in the chat. So be patient here while I figure that out. But yeah, somebody asked about doing a problem that requires a graphing calculator. Like I said, that's not really something you guys got to focus on at this point. Let's see what else. Did I miss anything? Okay, I'm just looking through the chat. Thanks for being patient. Okay. Oh, here's a question. Could you please explain some of the conceptual concepts like, okay, so there's been a couple of requests for mechanisms. So let me go ahead and do a mechanism problem. Okay. So I'm going to clear this. Let's see, for mechanism. Let me get you guys a good one here. Okay. So how about something like this? So let's say, so here's an example. So mechanisms, okay? Sorry, my handwriting is atrocious. So you guys, let's just say I have a reaction that looks something like this. Whoops, you know what? Hold on. A slight little detail there. Hold on, not quite what I wanted. Okay, so let's say peroxide plus, oops, sorry, plus 2I minus plus 2H3O plus. Okay, and I'm just pulling a problem from your book here. Whew, that's just kind of a big one. So let's say this is your overall reaction. Okay, kind of a big one. Hopefully it's balanced. Okay, and I'm going to tell you that this is a possible mechanism. Okay, so step one might look something like this. We take that peroxide molecule and react it with I minus. Okay, and it makes some kind of gobbledygook. Looks like this. Sorry, this one, it's kind of a lot of writing. I apologize for that. So give me a second. I'm writing as fast as I can. I forgot my stylus, so I'm just using my finger here. Makes the handwriting even better. Okay, step 3 of this mechanism. And somebody asked me earlier today, they're like, are all mechanisms 3 steps? Absolutely not. Lots of them are just 2 steps, sometimes even 1 step. So, but 3 steps does seem to be kind of common. Okay, so you guys, let's say these are 3 steps of a mechanism, and I'm going to tell you that this top step is fast. Nope, I'm just kidding. I'm going to tell you that this top step, I'm going to make this one the slow one. So this guy is slow, fast, fast. Okay, and that's the information I have. So I'm going to ask you the question, you know, some questions about this. So number 1, I'm going to say, okay, is this a good mechanism? Okay, and there's a couple criteria for the mechanism. First of all, it has to add up to equal the overall. Okay, and then second of all, the rate law. The second question I'm going to ask is, what would be the rate law for this reaction? Okay, so since I told you that the slow step was the first one, then you can write the rate law. Okay, so I'm going to go ahead and I'm going to take that slow step, and I'm just going to write the rate law. Rate law equals K. Okay, and I'm just, remember, the big thing with mechanisms is that the orders are determined by the coefficients. So we told you never to do that with overall reactions. So like right here, that's an overall reaction. You would not want to use the coefficients as orders, okay? But when you have a mechanism, that just means you're looking at like collision by collision. You're taking this big reaction and you're splitting it up into these smaller steps. Okay, so that's what a mechanism is. But you really want to look for the code words, because it will say, potentially this is a mechanism, and it will say, these are elementary steps. And as soon as you hear the term elementary steps, you need to know that, oh, okay, the coefficients are the orders, okay? So what that means for the slow step, I'm going to take that HOOH peroxide, and it has a 1 in front of it, so that means it's going to be first order in terms of peroxide. Sorry, that's an I minus. And it's also going to be first order in terms of I minus, okay? So what that means is that this is the rate law for this reaction, okay? So it is bimolecular, okay, because 2 things are colliding, and it's second order overall, okay? So far that's reasonable. That would be the rate law for this reaction, okay? That means the concentration is, or the rate is dependent on the peroxide concentration and the I minus concentration. but I can ask you guys some more questions about this. Okay, so first of all, you guys ready for the first question? Unfortunately, I wish I had a little more room on my screen, so I'm going to try to move things around a little bit. Whoops, that was not the right direction. Okay, so I'm sorry, I'm a little short on space. So my first question would be, okay, what would happen if you doubled, you guys, this is going to seem really weird, but a good question. What if you doubled the H3O plus concentration in this reaction? Okay, and what I would want you guys to say to that is there's H3O plus, it's part of the reaction, but guess what? It's not part of the rate law. So if you doubled the H3O plus concentration, guess what happened in this reaction? A whole bunch of nothing, okay? Because basically, if H3O plus is not part of the slow step, and therefore it's not part of the rate law, it's zero order in terms of H3O plus, okay? So that's one question I could ask. Second question I could ask is, if you look a little closer into this mechanism, are there any intermediates? Are there any catalysts? Okay, so intermediates, okay, and I'm going to abbreviate that. And are there any catalysts? Okay, hopefully you can tell that that word is catalyst. Okay, and somebody asked, they said, why are you not supposed to write an order of for H0 plus to be zero order? Guys, you know what? You could. Let me show you something. Okay, that's a really great question. If I wanted to, you know, this is the rate law, right? Okay, I mean, you could put H0 plus in there. You totally could. But as soon as you put a zero there, what is anything raised to the zero power? It's one. So anything that is raised to zero power really kind of cancels out. So you know what? It doesn't matter. If it's zero order, it's just not part of the rate law. Okay. So that's kind of how that works. So hopefully that answers that question. It was a really good question. Okay. So let's go back to this idea of intermediates and catalysts. So what crosses out? Okay. So I'm going to go ahead and switch colors here. So let's see. How about, does anything? Let's see here. Oh, HOI. Whoops, that's not what I wanted to do. Sorry. I put that back. I didn't mean to delete it. It's just meant to cross it out. Geesh. Let's try that again. Yeah. Okay. So this crossed out with that. That looks like that would be an intermediate. Okay. And there's some other intermediates. We got OH minus canceling out with 2 OH minus. That's another intermediate. Okay. So what's left? Let's see. It looks like we have peroxide plus I minus plus I minus. Sorry, I dropped those minuses. So that's 2 of them. Yields and plus 2H0 plus yields I2 plus 4 waters. Okay. So what crosses out are the intermediates. So the intermediates would be the HOI and the OH minus. Whoop, I probably shouldn't circle those because that makes it a little confusing, doesn't it? Okay, so instead of circling them, how about I'll put a box around them. So this is an intermediate and this is an intermediate. So OH minus, okay? As it turns out, there's no catalyst. Okay, and I kind of meant for there to be a catalyst, but that's okay. If there was a catalyst, okay, I just wanted to emphasize that with catalysts, it would be found on this side. So let's say it would be part of this step, okay, and then it would reappear down in another step, okay? So you guys will see a really great example if you haven't had class yet for your B day on page 32. On page 32, it has a great example of a catalyst. So a catalyst is there, it gets used to speed up the reaction, and then it reappears. Okay, so there's no catalyst though in this reaction because we don't. Okay, so we have 2 intermediates, but no catalyst. All right. Other than that, oh, there's one more parameter about this reaction is, well, I already showed it, that basically the 3 steps have to add up to the overall. Okay, so I'm going to recap. For a mechanism to be good, first of all, the rate law of the slow step has to match the rate law of the slow, whoops, let me try that again. The rate law of the slow step will match the experimentally determined rate law. In other words, it will be the rate law. And also that the steps of the mechanism have to add up to equal the overall. Okay, so that's a little bit about mechanisms. I hope that helps a little bit. I'm looking at the chat right now to see if there's any other questions related to mechanisms. Okay. All right, that looks pretty good. In general terms, what would be the units for K for that particular second order reaction? hopefully you guys are getting really good at just knowing the units for K. Okay, and just remember the units for K are always 1 over 1 molarity less than the overall order. So even for this one, if it's second order overall, what's 1 molarity less? That would be just 1 molarity. Okay, and then unit time. Okay, and I didn't really specify that in this problem, so I'll just leave it generic as unit time. Could be seconds, could be minutes. But that would be the units for K. Okay, all right. Hopefully we can put mechanism to bed, but let's see. Can we consider the catalyst if it only shows up in step 1 or 2 or 2 or 3? Does that have to start? And that's a great question. So you guys, a catalyst, it can be anywhere in the steps, as long as it starts as a reactant and then it gets used up sometime later. Doesn't really matter what steps it's in. It just has to start off as a reactant and end as a product. Okay, and like I said, if you want a really great example of a catalyst, refer to page 32. I think it's example 9. Okay, you'll go over in class if you haven't in class already. How would an intermediate show up on a graph? Okay, Sarah, I think I know what you're getting at. So, that's a great question. So you guys, let's say, I kind of like this one. So let's say this is 1, 2, 3 steps, and the first step is a slow step. I'm also going to add that we will say that this reaction is exothermic. I'm telling you that. That's not something you would have known. I'm telling you that this reaction is exothermic. All right, so I'm going to go to the next screen, if I can attempt to do that. Here we go. So I think, sir, what you're asking is how would you graph that? So let's say you had an energy diagram, and this is progress. Okay, so how would you graph that? So first of all, I told you that the overall reaction was exothermic. So that means your reactants would be here, your products would be here. Okay, so that's exothermic. Okay, and then it's 3 steps, right? So you're going to have 3 hills, but the first step was the slow step. Right, the first step was the slow step. So what that meant is that the first step is going to have the biggest activation energy. So I might be exaggerating this a little bit, but let's say it looks something like this. Okay. That looks a little weird. Let me fix that up just a skosh. I didn't mean to delete it. Oh no, let me try it again. So I'm gonna make this one big. Now you guys, there we go. That looks a little better. Okay, so you guys, just for showing activation energy, let's see. This would be the EA for the first step. Okay, so we'll call that EA1 for the first step. For EA2, okay, it's going to be the start of the new reactant level to the height of the hill. Okay, so that would be EA2. I'll quite have room to write that. And then this one would be EA3, okay, for the third step. I don't really have a way to tell if the second step or the third step, which one was faster. So, it's your guess is as good as mine. This is acceptable. The only thing that's a non-negotiable is this one. It had to be the biggest EA because that's the slow step. Okay. So what I see here is, let's see, what else could we pull out of this? That you would have one at the height of the tallest part of the hill. That's where you're going to have your activated complex transition state, meaning that's like the most unstable point in the reaction when you're like halfway between bond breaking and bond making. Okay, so the star here is called the activated complex or the transition state. And then you have 3 intermediate regions. Sorry, not 3, 2. Okay, the little dips right there, those are the intermediate regions. Okay, so that's kind of how I would analyze that. And then, of course, the one thing that just doesn't change is delta H. Is as long as your products are still the same and your reactants are still the same. All right, Sarah, was that kind of hitting the mark on what you were asking? Okay, so before I move on, are there any other questions about this mechanism or this energy diagram? Okay, all right. So you guys, that kind of opens us up to what other questions do you guys have? Yeah, so I'm gonna go ahead and delete this or go to a new page. How about that? Even more fun. So you guys, some tips. I would be able to do math without a calculator. So can I give you guys an example? Oh, okay, wait a second here. Wait a second. Can you do a rate law question with a rapid equilibrium? Yes, I can. How about something like this? So one more mechanism, okay? I don't want to spend too much time on it, but let's say, here's my mechanism. You wanted a rapid equilibrium. Okay, so we got a rapid equilibrium between Cl2 and 2 chlorines. Okay, and then let's see what else. So we got the next step of the mechanism would be something like this. Cl3. Okay, and then we'll do one more step. Okay, all right, so it might look something like this. Okay, so about this one, and I will tell you that this is the slow step. Okay, so the common types of questions I would ask you is I would say, oh, what's the overall reaction? Okay. So if you add up these three, what do you call it, elementary steps, okay, what crosses out? So let's see, 2Cl, we got a Cl here and a Cl here. And I think, looks like this guy crossed out with this guy. Again, I picked one that has 2 intermediates, but not a catalyst. Okay, sorry about that. Okay, so the overall reaction would be something like this. Okay, so the elementary steps add up to equal the overall reaction. And that's good. I'm just making sure that it's balanced. Looks pretty good to me. Now, here's, I think, what you're getting at. So what's the rate law for this reaction? Okay, so of course, I'm going to use the slow step. Okay, in the slow step, Cl first order, CHCl3 first order. Okay, and you think, okay, there's my answer. Okay, circle the choice, but that's not right, because Cl, this guy right here, is an intermediate. Intermediates tend not to be part of the rate law. Okay, and as a side note, I will say that catalysts can be. Okay, so if there was a catalyst that was part of the rate law, that's totally fine. Okay, but intermediates cannot be part of the rate law. Okay, so what do we do? So we say to ourselves, well, where did the chlorine come from? So that means you're going to have to go up a step further. Whoops, I'm going to change colors here. So we're going to go and say, well, where did the chlorine come from? So we're going to go up to this step. Okay. And you know what? We're basically just substituting in. But this one's a little tricky because let's see, I have 1 chlorine here, but I have 2 chlorines here. They don't match. So I can't quite substitute in. But I can fix this problem because how can I make a match? Okay, well, I can cut all these coefficients in half. So there's a 1 right here, so I'll just cut it in half. So you can do that. So this will cross out. So now I got 1 chlorine, okay, being produced from basically a half a mole of Cl2. Okay, so long story short, now I can substitute in. Okay, so I'm going to go ahead. I'm going to get rid of this, get rid of that. Okay, and say, well, where did this intermediate come from? It came from Cl2. Okay, and this is still an elementary step. Okay, but there's a coefficient of a half in front of the Cl2. Okay, now I know that looks kind of weird because we haven't really come across half orders too often, but all things considered, they're actually fairly common. Anytime you have an intermediate in your rate law, and you kind of gotta trace it back to where the intermediate came from. So you guys, that's totally just following the rules of good mechanisms, and that's allowable. Okay, so now we would say that it's first order in terms of CHCl3, and it's 1/2 order in terms of Cl2. Folks, I do not expect you you can still do math with that, okay, with half orders, you can crunch all the numbers the same way. We're not going to do integrated rate laws with half orders or anything kooky like that, but just know that this is acceptable, okay? So that would be, I think, a good example, okay? So I'm going to look at the chat. If you need some further clarification on this problem, let me know. Let's see. Can it be considered a catalyst? Okay, we answered that question. Okay, I'm looking at the chat. Hopefully I'm not missing anything. Did anyone have any other questions about this example? Okay, so hopefully we can sort of leave mechanisms for a little bit. What do you guys think? Okay, so let's see, what other examples? So I'm looking at the chat to see if you guys can inspire me on what I should maybe go over next, but I can't do a problem. I think this is a problem that you guys might enjoy because it involves not using a calculator. Okay, so I'll say something like this. Let's see. How about, I kind of really feel like just typing this. I wonder if that would work better. I'm gonna go ahead and try the text feature. Oh man, this is money right here. Let's see. Ooh, that feels good. The half-life for a first order reaction is 3.5 minutes. What fraction of a sample would remain after 15 minutes? Okay, how does that look? Okay, and I'm going to add to it, no calculator. I'm going to give you some choices. Okay, so A, I don't know, 0.07, a fraction of 0.07. B, how about 0.05? C, 0.02. Whoops, that's a 4. That's a 3. There we go. And maybe D, 0.01. Okay, so you guys, the challenge that I'm giving you here is, ooh, how would you do this? Okay, before I do that though, somebody asked, could you explain why the enthalpy doesn't change? Okay, so I'm gonna go back to this slide real quickly. I think you're asking about this one, Irene. Can you explain why the enthalpy doesn't change? Okay, so basically asking why this doesn't change. Whoops. And the story with that is because your products are still the same and your reactants are still the same. So delta H is just not going to change. Okay, delta H is determined by the difference in the product, product level minus reactant level. Okay, so that's it. Delta H. I mean, this chapter is not really about delta H, so I really can't really think of any factor that's going to change delta H. Okay, so everything we do in this chapter, delta H is just kind of set. Okay, it's the difference between the product level and reactant. Okay. All right, so I'm going to go back to this problem. Maybe I gave some of you guys some time to think about it. How would you do this without a calculator? Okay, and actually I think what would be kind of interesting is, could you do this with a calculator? And could you do this without a calculator? Okay, but we'll start without a calculator because for first order kinetics, what I really like to use is time amount tables. I mean, whoa, you do not need natural logs to do time amount tables. Okay, so what that means is that the beauty of first order is that that half-life is not going to change. Okay, and it doesn't matter what you start with. So no matter how much you start with, it's going to take 3.5 minutes to cut the sample in half. Okay, so what would remain after 15 minutes? Well, I'm going to start with my full amount, and I'm going to start at time 0. Okay, and then I'm just going to keep doing a bunch of half-lives until I hit around 15 minutes. So I'm going to cut this in half. Okay, and then 3.5 minutes has elapsed. Okay, and then I'm going to cut it in half again, 0.25. 3.5 minutes has elapsed. Okay, so that's my first half-life. That's my second half-life. Okay, I can keep going. I think you guys see how this is going to work, but I think this is a pretty powerful technique when you can't use a calculator. So now we're looking at 0.125. Okay, and that would be what, 10.5? Okay, so another 3.5 minutes later, so that's my third half-life. We're getting close to 15, right? So let's do another one. So now we're at 0.065, I think, 5. Okay, and let's see. So another 3 minutes, 13, so 14, that would be at 14 minutes. So that's my fourth half-life. Boy, I'm getting really close to 15 minutes. Okay, so now I'm going to do one more half-life. That's going to put me at what, 17.5? Okay, and I'm going to cut it in half again. That's going to be 0.03 125 or whatever. Okay, yes, you guys agree? So basically, in order for this particular reaction, okay, the half-life of 3.5 minutes, basically, give or take, a little less than 5 half-lives have occurred. Okay, because 15 is going to put us like right in here someplace. So I think you guys picked the best answer. Okay, so what fraction would remain after about 15 minutes? What are you guys thinking? Right, it's going to be between 0.06 and 0.03. Okay, so this guy's out, this guy's out. Looks like that's our winner. Okay, 0.07 would be in there someplace, so that guy's out. So what do you guys think? You guys can use? You guys like time and amount graphs? Okay. But you guys, just the same, could you guys do this problem, of course, with a calculator? So if it's in the short answer, of course, you could do it this way, but you could solve for it a little more accurately. So if you know the half-life's 3.5 minutes, Guys, I'm telling you, for first order, this little formula, it's on your equation sheet, is awfully helpful. So if you know the half-life, then you can figure out K. So if I go ahead and, plug in 3.5, okay, and divide by K. All right, so I'm gonna go ahead and multiply both sides. I probably don't need to show you guys the algebra, okay, but what the heck? So looking something like this. So if you're gonna solve for K, looks like it's gonna be 0.693 divided by 3.5. Okay, so we can use a calculator for this one. So if I punch into my calculator, that looks like it comes out to like 0.198. But what are the units? Please don't forget units. So this is first order, you guys should have the units memorized. Okay, units for first order, 1 over 1 less molarity than the total order. So it's first order. So if you get rid of that 1 molarity, it's just going to be 1 over unit time, which in this case is minutes. Okay, so that's a silly little thing, but don't forget that it's not always seconds. Okay, so that would be K. And then of course, can you guys go ahead now that you know K? Can you solve for what this would be after 15 minutes? Okay, so I'm going to make a little more room here if you don't mind. Okay, and now you guys can just use the integrated rate law. Okay, so let's see. So natural log, natural log of X, like what would remain? Negative KT, and I'll go ahead and just plug those numbers in. Okay, so 0.19, sorry, 198, 1 over seconds, sorry, 1 over minutes, right? And then after 15 minutes, okay, and then plus natural log of your starting point, which we decided to start with the full amount. You guys could easily do that, right? So I think X comes out to, if I did this right, how about 0.0513, okay, which is pretty spot on to what we were talking about, right? So in terms of fraction, 0.0513 would remain over 1 as the total. So the fraction would be 0.05. Okay, 0.05. Does that make sense? Okay, so you guys, I don't know, give me some feedback. Okay, was that helpful? Because that's something you're gonna have to do, is be able to do that type of time and amount graph, to do calculations without your calculator. Okay, are we good? All right, guys, what other questions do we have? I'm gonna make sure I'm not missing anything in the chat. If I could find the chat, I think I kind of lost it. Hold on. I have the chat, but I lost it. There it is. Okay, so you guys, the last question I'm seeing in the chat was, can you explain why enthalpy doesn't change? Am I missing anything? Because I hope I'm not. Right, let's see. Okay, so what else do you guys have on your mind? So I'm gonna do that awkward pause. Okay, in fact, I'm gonna stop sharing my screen for a minute so I can see all your beautiful faces that are actually kind of just like black squares. Okay. But I'm just going to give you guys a second to sift through your binders. What else are you guys interested in? Okay. Let's see. All right, guys, what other questions? So you guys, some tips. I'm going to go back to sharing. You guys, let's see. Obviously, for the test on Thursday, you want to make sure you know those graphs. Okay, so when I say those graphs, you know what I'm talking about, right? So I'm going to close this 1 second. I'm going to share my screen, but I'm going to go back. I'm going to go back here. Nope, that's popcorn order. That's kind of funny. There we go. You guys see that okay? So when I say make sure you know your graphs, like don't memorize the summary, okay? But make sure that you understand, how basically all these graphs relate. I told my students that I like to start at the bottom sort of and just kind of go upward to say, okay, what are all the things I can understand about second order? All the things I can understand about first order. Okay, so I'll give you guys a couple examples. They're going to kind of come from the summary. Okay, so if you have it out, you might want to pull it out, I guess. Okay, so I'm gonna stop sharing again and go back to the whiteboard. Okay, so for instance, how about something, ooh, that's a good one too. How about something like, how about first order, second order, zero order, right? What happens to K? What happens to half-life? Okay, and this one, how about if you double concentration of a reactant, what happens to the rate? Okay, so you guys, this should be really easy, okay? But like, let's just make sure that you sort of have your basics about these orders, okay? And you guys, you know what? I'll tell you what, the one thing, since you guys are all here, is I'll be mad at you, okay, if you get this one wrong. When it comes to K, okay, what is the only factors that will ever change little? So basically, the only things that will change the rate law constant is, let me write this down in a different color. If you increase the temp, guess what's going to happen to little k? The rate law constant will go up, okay? Right? And I hope that makes sense, because if you think of any old rate law, doesn't matter which one you look at, if you increase the temp, and you guys, why does temperature increase rate? Okay, for two reasons. I would know both of them. If you increase the temp, you're going to increase the number of collisions, and you're going to increase the force of collisions. So that's why temp is sort of a double whammy. So if you increase the temp, yeah, you're going to have more effective collisions, more collisions that can get over the activation energy. So the rate's going to go up, but the concentration stays the same. So that means K has to go up as well. Okay. So if you increase the temp, K is going to go up. Okay. And the other one is if you add a catalyst, and an appropriate catalyst. I mean, not every reaction, you know, can have a catalyst, but if you add a catalyst that's appropriate for a reaction, okay, then you will increase K. Because again, the rate's going to be faster, but the concentrations are going to be the same. So that means K has to increase. So that being said, for first order, second order, zero order, only if you keep the temp constant, then K is going to stay the same, as long as the temp stays the constant. Okay, and then for a reaction at temperature, okay, what would happen to the half-lives? So T1 half. So for first order, it would stay the same. For second order, as you go through a reaction, the half-life continually doubles. So if the half-life was 10 minutes when you cut it in half the first time, it would be 20 minutes. You cut it in half the second time, it'd be 40 minutes when you cut it in half the next time. Okay, and then zero order, the half-life cuts in half. Okay, and for zero order, that makes the most sense, because if you have a reaction and you cut the concentration in half, let's say it takes 10 minutes, but now you have half as much stuff. So to cut it in half again, it's going to take 5 minutes. Now you got a quarter of as much stuff. So to cut it in half again, it's going to take like 2.5. Okay, you guys see how that works? Okay, and then finally, if you double the concentration in its first order, then what would happen to the rate? It would double. If you double the concentration at second order, what would happen to the rate? It would quadruple, right? Because it's squared function. And if you double the concentration, what would happen to the rate for zero order? Stay the same, right? Okay. So guys, that's, I mean, I'm definitely going to ask this question, and, you know, that's kind of the summary of first, second, and zero order. Okay. All right. So let's see. I had a question about that. Let me see. I'm going to switch to another screen here. Now, something else, kind of why we're talking about those graphs, is, you know, you got your zero order. Okay, you got your first order, and you got your second order. Okay, and this is the half-life. You guys call it the half-life graphs. I just call it like the raw data graphs. You know, like we're just sitting here watching the reaction happen. Okay, and of course, zero order is the straight line. Okay, and then first order is a curve, and second order is like a curvier curve. Okay, and one of the things that I could ask you is, how could you prove that in a first order reaction, it's a curve, right? So how could I prove that the rate starts out fast and then it slows down? Okay, and you guys might remember that you would have to do a tangent line. Okay, do that tangent line. So let's say at this point right here, we'll call that, time X or whatever. If you do a tangent line, you see that the slope is really steep. Okay, and that's because the rate is really fast. Okay, at the beginning of a reaction, the concentration is high. But then as the reaction proceeds, whoops, that's kind of silly. Ooh, that's a really nice tangent line. Okay, if you draw a tangent line there, you can just see that the slope is flatter. Okay, and that's because as concentration goes down, the rate went down. Okay, so that slope indicates that it's a slower rate. And you can do the same thing with second order. There's no question about it. You could do, and you guys, that's called an instantaneous rate. Okay, a slope of a tangent line is that rate at that moment. Okay, so it's proving that the rate is changing over time. The rate is changing over time. Now, of course, zero order, what you wouldn't have to do that because it's already a straight line. So the rate is constant throughout the duration of the reaction. It's not changing. Okay, so you wouldn't need to do a tangent line or anything like that because it's already a straight line. It's already a linear relationship. Okay, so hopefully you guys kind of remember how to do that. That's sort of going back into like some of the early stuff we learned, like how to do tangent lines. Okay. Let's see, what else do we got? Somebody asked about temperature and catalyst. Let's see, I can do that. So let's see, let's talk about catalyst. So let's say you guys have an energy diagram. Okay, so there's energy and there's progress. Okay, and first of all, exo. Hopefully you guys are yelling at your house, exothermic, right? Because delta H, okay, it goes from high to low, so that's exothermic, okay? So if I showed the effect of a catalyst, okay, I know you guys would know that, you would basically lower the EA, okay? So the hill's lower, okay? That's one way to show it, but just so you guys know, I mean, there's other ways. Okay, so another way would be, you could lower the activation energy by, instead of doing a one-step process, what if you did like a two-step process? So it might look something like that. That's fine too. It's got two steps instead of one, but still the collective activation energy is lower. So boom, it's an alternative pathway and it's good. Okay, so that's fine. Okay, but also another way is, this one's totally different, is you guys could do a Boltzmann distribution curve. Now, if you haven't had chemistry today, like my fourth bell, sixth bell, or Ms. Schneider's sixth bell, I think, we're probably going to talk about this a little bit more tomorrow, okay? But a Boltzmann distribution curve is where you have number of molecules on the Y, and you have like energy on the X, okay? And so like a distribution might look something like this at like room temp, okay? But so if you guys remember, for a distribution curve, let's say this represents 1,000 molecules, okay, 1,000 reactant particles. Okay, then what you'd see is that, well, they're not all traveling, they don't all have the same energy. Okay, the average amount of energy is like the top of this hill, like that's the average. Okay, but some particles are moving slower, some particles are moving faster. Okay, so do you remember how distribution curves work? Okay, so I'm gonna get rid of that. And now here's the part we're gonna tie the kinetics. Okay, I'm going to put a very distinct energy on this graph. So I'm going to come through and I'm going to put a line right here and I'm going to say that is the activation energy for the reaction. So in other words, I'm going to go back over here for a second. Let's go back to the uncatalyzed. This right here, the EA, is a certain amount of energy, right? Well, guess what? That same energy quantity, let's say it's like 350 kJs, is right here. 350 kJs, okay? So this and this quantity are like the exact same, okay? So we're just showing it differently. So what you see here is that all these particles that have more energy than the activation energy, they can produce effective collisions. Like they have enough energy to get over the activation energy, okay? And all these guys, which I'll show with yellow, okay, they're colliding, but they're not colliding with enough force to get over the hill, okay? So, I mean, roughly, I might say that, what percentage of particles are to the right of that line? Maybe like 17%. So of all the collisions like that these 1,000 particles are doing, 17% of them are effective. Okay. So now the question might be, how could you show the effect of adding a catalyst? Okay, well, on this graph, as we just showed a minute ago, you would lower the hill, right? How do you lower the hill on a Boltzmann distribution curve? Well, you would shift this EA this way. So what if you put the EA like right here? So that might be EA for, sorry, just make place here for a catalyzed reaction versus the blue one is EA for an uncatalyzed. Okay, so what you see now is that all of a sudden, well, gosh, now all these particles and these particles all have enough energy to overcome a smaller hill, right? A smaller hill. So you guys see how, gosh, both these are great ways to explain how a catalyst speeds up a reaction. Okay, what do you guys think? Okay, so that's catalyst. If you want to talk about temperature, okay, so let's see here. I'm going to go ahead. So that would be a little different. I'm going to go back to my original distribution curve. Okay, so basically I'm just going to erase everything, evidently. Okay, all these silly little lines here. Go away, go away. Okay, what if I did something like, you know, here's my distribution curve. Same one, this was at room temp. Okay, and then, oh gosh, well, let's say, okay, and let me put my EA back in, sorry. So there's my EA value. Okay, so this percentage of particles can get over the hill. Okay, well, what if I increase the temp? Well, the EA is not going to change, it's the same hill, but what is going to change is my distribution. You guys see? So now, instead of just this many, okay, now all like almost 50% of the collisions are able to overcome that activation. So you guys, when you start talking about temperature, you shift the distribution. When you're talking about a catalyst, you shifted the hill. You made the hill smaller. So hopefully you guys can kind of see the difference with those. Okay. Okay. Looking to see if there's any questions about that. So can catalysts form no Helmholtz one? Okay, so that's a good question. So can catalysts form no Helmholtz one? Someone asked a question about catalysts. I think that's true. Okay, I'm not quite sure what you're asking, but I think it's true. Okay, so I'm gonna go ahead and erase this. Okay, what other questions do you guys have? Let's see. It said, could we quickly review rate versus first, second, and zero order? Okay, so I think what I see there, and I think what we're asking is I'm going to go back to zero first and then second. Okay, so I think this is like on your summary sheet, this is like the top one graph. It's the first one we ever thought about. So it's rate versus concentration. Yeah. Okay, so you guys, I can't emphasize enough, make sure you really pay attention to your axes. Whoops, rate versus concentration. Okay, and you guys, zero order, you know, the funny thing is you should understand this so much better now than you probably did at the time. Okay, but zero order, you guys know that as concentration goes up, as concentration goes down, it just doesn't matter, the rate stays the same. So that's why it's that horizontal line. Okay, so that is really the exact same thing as saying that concentration versus time is a straight line like that. Like, those are not, those are saying the same thing. Right, the second one that I drew, remember change in concentration, so like this change in concentration over change in time, right? That is rate. Okay, and it's a straight line, and that would be the value. So, you know, I want you to see the connections there. Now for rate versus concentration for first order, of course, it goes up directly. If you double the concentration, the rate's going to double. If you quadruple the concentration, the rate's going to quadruple. Okay, so that's a nice linear relationship. And then for second order, it's a squared function, so it ends up looking like a curve. In other words, if you double the concentration of A, the rate quadruples. So it's just when the concentration goes up, man, the rate really increases. So it's a curve. Okay, so I hope that helps. I think that's probably what you would need to know. Okay. Let's see. I think before we leave, let's see, I guess I have 2 points that I think might be helpful. Let's see, where were they? One of them is, okay, so this one, it's just something I bet that you maybe haven't thought about. So factors that affect rate. Let's see what you guys think of this. Okay, and I'm going to give you kind of another little table here. So let's say we're reacting magnesium plus HCl. Okay, so we're doing the classic single replacement reaction to make hydrogen gas. Okay, and I'm just going to ask you, let's see, I think there's a 2 right there. I'm just going to ask you what factors would increase the rate of this reaction. So here's your choices. Let's see. And I'm going to tell you that, like, we're going to start with magnesium strip, okay? Like, you know, like magnesium ribbon that we use. And we're going to start, whoops. Enable, okay. And we're going to say for the HCl, we're going to use like 3 molar. Okay, so that's what we're going to start with. So how can you make the reaction rate faster than these conditions? Okay, so here's some choices. Choice 1, how about use, okay, and I'm going to add to it, we're going to use 10 mils. Okay, so that's what we're going to start with. We're going to use 10 mils of 3 molar hydrochloric acid. If you guys have done this reaction before. So which of the following choices would most increase the reaction rate? How about use, I'm going to make this look a little nicer. Uh-oh. Who can see this transcript? Uh-oh. There we go. I'm just going to make it a little neater here. Okay, so how about first choice? What if you use 20 mils of 3 molar hydrochloric acid? Next choice, what if you use 10 mils of, how about 4 molar HCl? How about use Mg powder? Increase the temp. Okay, so I'm going to give you guys those choices, and I'm going to change the question. I'm going to say, which of those 4 choices would not increase the reaction rate? Okay. And I hope that you guys are thinking about it. And, you know, what I really want you guys to see is like this one here. This time, you know, you're using a higher concentration of HCl, so that's going to be more collisions. Okay. So that's going to make the reaction rate faster. Okay. But using more of the same concentration, folks, that is not going to make the reaction rate faster. Okay. Because you know what? The collisions are still the same. Okay. Just because you have, you know, double the volume, okay, it doesn't mean that you have double the number of collisions in that space. So I gave you guys this question. It was kind of a long buildup, but the truth is it really has to be an increase in concentration. It's not enough to just have an increase in amount of stuff, same concentration. Okay. Of course, you use magnesium powder. That would increase the reaction rate because you're increasing the surface area. Okay, and increasing the surface area means, I like to say, you have more exposed reactants. Okay, when you have smaller pieces of powder. And you guys, of all these changes that I did, probably increasing the temp. You know, I didn't really specify how much, but usually increasing the temp has the biggest effect. Okay, and we talked about that a minute ago. The 2 reasons why increasing the temp increases the reaction rate is because you increase the number of collisions and you increase the force of collisions and increase the force. Okay, so you guys, that's kind of a double whammy. Okay, and that's why you're really going to increase the number. Okay, so that was the fun one. I wanted to throw that at you guys real quick. And I guess the last one, I kind of had this one on my mind. I'm going to clear this out or go to the next page. How about that? In case you guys have a question. Is, okay, without a calculator. So let's talk about without a calculator. So I'm going to give you guys a reaction. 2A plus B yields A2B, let's say. Okay. And I'm going to give you guys some data. I'm going to say, let's see. And rate of disappearance. Just takes so long to write. I'm sorry. Rate of disappearance of A. So that's what we're tracking. Let me get rid of that. And then we're just going to plot concentration of A. We're going to plot concentration of B. And we're going to do a couple trials. 1, 2, 3. Okay, so let's see. So for the first one, 0.0002 is the rate, and we'll say that's in molarity per second. Okay. And then concentration A is like 0.001 molar and B 0.1. Then second trial, we're going to keep the B constant, but we're going to make this 0.001. And this is going to be 0.002. And then our third one, 0.009, 0.002. Sorry, this is taking such a long time. I should have had this one prepared ahead of time. Okay, and this one, I'm finally getting to a point, I promise. .024, and then we'll say 0.03, 0.003, and 0.2. Whew, that took a lot. So yes, you can probably guess what I'm going to ask. What's the rate law? Okay, I chose this one for a reason because I want you to do it without a calculator. Okay, and there is something kind of special about this one that maybe you haven't seen in a while. Okay, so let's give it a go. So, and this might be kind of the last one I do. So if you got questions, man, you better get in that chat. And if I'm missing, I'm just not seeing a lot in the chat. So I kind of feel like I'm missing some of the chat. I'm not sure. So let me know if that's the case. I'm sorry, but yeah, just pop it in the chat. Okay, so you guys, going back to this problem. So obviously, is this differential rate laws or is this integrated rate laws? I hope that you're saying, you're yelling, differential rate laws, differential rate laws. Okay, because I gave you a bunch of different trials that changed the concentration, and then we saw the effect on the rate. What trials do we want to compare? Well, I see that B is held constant, trials 1 and 2, and then this is without a calculator. Okay, how is trial 1? Well, how is A changing? So it's going from 0.0001 to 0.001. So that's a times 10 change, and then what's happening to the rate? 0.0002 to 0.002. Is the times 10 change. So it's being kind of mean there because you don't usually see a times 10 change, but it's okay. So hopefully you guys agree that it is first order in terms of A. Okay. So you guys, we're doing this without a calculator. So, you know, I'm kind of, just kind of eyeballing the numbers. Okay. Now this is why I picked this problem, because how are you going to figure out B? Problem is A is never held constant. Okay. So you look down the line, A is never held constant. So that's okay. Okay, and you can do this without a calculator. Okay, so as long as you know that what A is, what order it is, okay, you can figure it out. So I'm going to pick the nicest numbers. So I'm kind of thinking that maybe I would like to compare trials 1 and 3. Okay, and the reason why I picked that is because, you know, B is doubling, and that's a really easy number to work with. That's a little easier than like increasing by a factor of 1.5. But it doesn't matter. But without a calculator, I'm going to go for the easiest possible numbers. Okay, and A triples. So you guys, we're doing this without a calculator, right? So what I'm going to do is I'm going to apply the effect of A being first order. So I'm going to triple it. So this concentration triples. So I know that this rate has to triple. Do you guys agree with that? Because A is first order. So if you triple the concentration, then the rate's going to triple. Well, guess what? I can triple this rate. So 0.002 tripled is 0.006. So I call this sort of like an intermediate rate because I'm only taking into account the effect of A being first order. Okay, so I tripled the concentration of A, so the rate tripled. Now I can take this rate and see, okay, well, what about going to this final rate? Okay, so then that's the effect of B. So let's see, B is doubling. Okay, and what do you see going on here? 0.006 going to 0.024. Well, that's an increase of times 4. Okay? So if you double the concentration of B and the rate quadruples, okay, it looks like B is going to be second order. Okay, so what do you guys think? So I just want you guys to see that this might be doing kind of a harder differential rate law question because A was never held constant. You can still do it. Okay, so I just thought this was a little technique that you could use, okay, without a calculator. So any questions about that? I don't see anything in the chat. So I'm assuming that's good. I'm going to close the chat and make sure I'm not missing anything. Oh, that's going to make me leave the meeting. I didn't want to do that. So I closed the chat and now I'm reopening it. Okay, I don't see any questions on that. All right, you guys, from here, I just want to remind you of one other thing that would pop up for sure is, guess what? So now that I know this is the rate law, good for me, woohoo. I might say something like, oh, by the way, for trial 3, okay, what is the rate of disappearance of B? So let me type that out, what I'm asking. I lost. Sorry, I have a dialog box that popped up and it's making me cry. There we go. So I'm going to get rid of this. I just need to make a little more room. So the question, I'm going to type this one. It would be something like, oh, right. Isn't that what I just said? Okay. For trial 3, what would be the rate of disappearance of, what would be the rate of disappearance of B in trial 3? Okay, and I just wanted to remind you guys that, oh my gosh, those are like the easiest questions ever. So what jumps out to me there is that I say to myself, let's see, this table is in terms of disappearance of A, but all of a sudden this question's asking me about B, okay? So that totally means that we're gonna do some kinetic stoic, okay? So if I look at trial 3, the rate is 0.009, okay? And that's molarity per liter per second, and that's in terms of A disappearing, okay? And then for every 2 moles of A, guess what? 1 mole of B is gonna disappear. Okay, so I basically cut that in half, so 0.0045. Okay, and then you can put it back into molarity per second, back into units of rate, and that would be in terms of B disappearing. So you guys, a little blast from the past, that's your kinetic stoic, so I just wanted to remind you guys how that works. Okay, so I see somebody that said, oh, all of a sudden a lot of messages popped up. But not too many. It said, why wouldn't the reaction increase with an increased amount of HCl? Because wouldn't there be more moles of HCl to react with? Okay, so let's see. I'm gonna go back to this question for a minute. So, okay, you guys know what? I think how kinetics is, it's not really about limiting reactants, okay? So there's some assumptions being made here that, that you have plenty of HCl to get the reaction done, okay? And plus you're adding more, okay? So it's not like you're gonna run out of HCl because you're adding more of it, okay? So that just means like HCl is just gonna be more in excess, okay? So that being said, limiting reactants and really the stoichiometry piece is kind of a non-issue, okay? So we're talking about reaction rate, which is just how many collisions happen per unit time, okay? So hopefully that answers that. Yeah, so again, there would be more moles of HCl, but because, it kind of be like this, like, let's say this is like my 20 mils of 3 molar. Okay, it's going to be spread out like this, okay? But if I have 10 mils, so half as much, 10 mils, but a 4 molar, I'm exaggerating this a little bit, it's more crowded, okay? And that's what's going to increase your reaction rate, is more collisions in a unit space. So it's all about concentration, okay? It's not really so much about total number. All right, hopefully that answers it. If not, jump up with me chat. Could you tell us again what the best page numbers to practice would be? So I'm going to go to another page here. I think my favorite review is page 41, 42. That's like the official kinetics review. I like page 23 to 24. If you're really into problem solving, okay, it's some pretty creative, just kinetics problems, going to sort of feel like OWL a little bit. Other than that, those are my favorites. And I would say, make sure you review page 1 and like the concepts, okay, and make sure you didn't miss anything, and just really review your notes. Especially going all the way back to like the introductory activities. Like when we first introduced kinetics, you're probably like totally lost, but if you go back now, it'll make a lot more sense. So I would definitely spend some time doing that, okay? That's what I would do. I think the no calc practice is really spot on too. So make sure you get all your questions answered there. Okay, and for my, I did make a video going through all the no calc practice, so that's going to be made available. So you're welcome to watch that if you want. And somebody said you might be missing questions for people who, so maybe who, okay. Somebody said maybe I am missing some chats. I'll go back. Ooh, so yeah, I'm on 2 different computers. So if you direct message the wrong me, I guess I might not have gotten your message because they're kind of going on my other computer. So let me just sneak through the other chat. Okay, so one question, I can say this real quick. It says, can we go over which factors change K? And again, if you increase the temp, you're going to increase K. And if you add an appropriate catalyst, you're going to increase K. Those are the only 2 factors that will ever change the rate law constant. Concentration does not change the rate law constant, nor does pressure, because pressure might be what you use for gases. Pressure and concentration are more or less the same. Somebody asked, can we use a calculator on the short response? Yes, absolutely. But a graphing calculator, yes, you can use it. You don't really need it. We're not going to ask you to graph anything. Okay. Sorry, I did miss some of these questions. Do we need to know how to write steps one? Okay, somebody asked, like, basically, do you have to come up with a mechanism? And the answer is no. It would be given to you. The basic thing with mechanism is you just have to decide if it's a good one. So you have to make sure that the rate law of the slow step matches the experimental, and you have to make sure that the steps add up to the overall. Catalysts are not always found in the slow step of the reaction. I would say they are. For mechanisms, the catalyst probably will be found in the slow step. There's other catalysts that we would show them in a different way. They wouldn't be part of mechanisms, like solid catalysts that aren't really part of the mechanisms. Okay, so if you're doing a mechanism and there's a catalyst, it's probably part of the slow step. Okay. If we had to find, so somebody asked a great question. Kavya said, if we had to find the overall reaction from a mechanism, would we write in the catalyst or would you leave it out? You know what? You would write the catalyst for the arrow. So it's still crossed out, okay, like an intermediate, but in a different way. And you would just write it over the arrow in the overall equation. Okay, I did that. Sorry, I'm just going over the chat. Units. Okay, thank you. Okay, thank you. I guess I was missing some of the chat questions, but I think I kind of got everything because you guys were savvy enough to ask the questions in different ways. There's a key for page 41, 42. If you can't find it, let me know. I'll make sure it gets there. And there is a key for page 23, 24. There should be a key for everything. So if you find something and there's not a key, just let me know. We'll make sure. I did see a question that popped up earlier that I was going to go over. Oh, I know what it was. Okay. I'll do one more thing because somebody asked about it in the chat. Okay. Is somebody asked, let me see if I still have it here. Bloop, bloop, bloop. Okay, I'm just going through here. Darn it, I got rid of it. Boy, I would say these slides kind of look like the Easter Bunny was like slaughtered in a vicious murder. Okay, all these colors. You guys are very patient. Okay, real quickly. So I'm going back to the half-life graphs. Okay, 0, first, and second. Okay, and of course, 0 order is a dead giveaway because it's a straight line. Okay, but first and second, they both look like curves. So somebody asked, how can you tell the curve from a first order and a second order? I actually think maybe the better way of doing this is I'm going to close this. I'm going to go back to this. Okay, this is the summary. And I think if you guys, I wish I could make this bigger. Oh, I did make it bigger. Look at me. I can't really draw on the screen, but I'm looking at the first order graph. Half-lives. Half-lives are the dead giveaway. So for first order and second order, they're both curves. But for first order, if you look at the half-life, sorry, it's going to be constant. So if it's 5 minutes for the first half-life, cut it in half again, it's gonna be 5 minutes. If you cut it in half again, it's 5 minutes. Cut it in half, 5 minutes. So that half-life stays constant. For second order, you are distinctly not gonna see that. Okay, so if like the graph I have here, the first half-life was 1 minute, but then to cut it in half again, it took 2 minutes. So that brought us up to 8 minutes in total. And then to cut it in half again, it took 4 minutes. So the next half-life happened at 7 minutes. And then for the final half-life, it took 8 minutes. So you guys, you see the half-life is kind of a dead giveaway. So if you can somehow track some piece of the half-life, then you'll have it. Okay. Let's see. Well, you guys, guess what? I think that puts us a little past an hour. And if you guys, hopefully some of you guys are coming during Connect. Don't hesitate to ask for clarification on anything I went over that didn't make sense to you. And I wish you guys luck on preparing, okay? So remember, the best piece of advice I can give you is get a good night's rest on Wednesday. And for heaven's sakes, there's no dumb question except for the one you don't ask, okay? All right, well, I think I'm gonna leave, but I'll wait a little bit. So if you have some question that you still wanna ask, I'll linger here for just a little bit, okay? But you guys have a great night. I appreciate you guys hanging with me. Yeah. You're welcome. I appreciate all the thank yous. Okay. All right. Looks like me and me.